In this video, I will summarize a paper that I wrote together with Edvard Mörtsell with the title Constraints on Bimetric Gravity from Big Bang Nucleosynthesis. So first of all, what is bimetric gravity? Well, in fact, it is an extension of general relativity, GR. So, in GR, gravity is massless, which means that gravitational waves propagate at the speed of light. So a natural extension of this theory is to give the graviton or gravity a small mass. And this is in fact bimetric gravity. In fact, in bimetric gravity, we have two types of gravitational waves, or two gravitons, if you like, one which is massless and one which is massive. And to achieve this setup, we introduce two metrics, or two spin 2 fields, if you like, G and F. But these metrics are not aligned with the mass eigenstates. And the mixing angle is denoted by theta. So this is very similar to neutrinos whose flavor eigenstates are not aligned with their mass eigenstates. The mass of the graviton we denote by MFP, FP for Fierce-Pauli. So what we want to do in this paper is to constrain the theory parameter space. So for example, these two parameters, the mixing angle and the graviton mass. In particular, we want to know whether or not observational probes push us towards the GR limit of this theory. That is to say, when the mixing angle goes to 0. Or if we can have some interesting modifications to GR while still being compatible with observational tests. So in this paper, we use the observed abundance of helium-4 to constrain the expansion history of the universe, and hence also to constrain the theory parameters of bimetric gravity, because they will determine the expansion history. So now the helium-4 was produced when the universe was very hot, so around MeV temperatures, and the abundance of helium-4 is in fact sensitive to the expansion history of the universe at this stage, in this phase. So in fact, one can derive this constraint on the Hubble parameter, that is to say the expansion history or the expansion rate of the universe. So here we have the ratio of the Hubble parameter in bimetric gravity and in GR, and it should satisfy this constraint. So this we can use to constrain our theory parameters. So we scan the whole theory parameter space and exclude all those points which violate this constraint. And this is the result. So here we have the mixing angle and the graviton mass. And the blue region here is the region which is excluded because it's incompatible with the observed helium-4 abundance. And what we can note is that, in fact, this gives us a factor of 2 improvement compared with other observational probes, at least out here, where the graviton mass is a bit larger, but still very small compared to standard model particles, of course. Now, so it's interesting to observe that even taking all observational probes into account, including the helium-4 abundance, which we analyzed in this paper, but also including, for example, solar system tests, gravitational wave observations, cosmological data from the cosmic microwave background. Even if we take all these observational probes into account, we are still not pushed towards the GR limit of this theory. That is to say, towards managing mixing angles. So for example, if the graviton mass is greater than 10 to the minus 18 electron volts, we can still go up to mixing angles like 15 degrees, which is certainly not negligible. Certainly not GR. Or for smaller values of the graviton mass like this, we can even go up to mixing angles of the order 30 degrees. So the conclusion is that we are not pushed towards the GR limit of this theory, and hence this theory can provide interesting deviations or modifications to GR while still being compatible with observations.